So this is the example they give. So they call it typical boundary conditions for one-dimensional 1D heat flow. And what they show is, okay, you got the rod, like so, and it's insulated on the sides, insulated on that side. And they say, well, you know, it might be insulated on the top, and then be put in a bath where I think this is 20 degrees Celsius. And so, you know, if you look at something like that, then a PDE, so the diffusion factor, U sub XX, and they said this is 200 centimeters or 200 millimeters or something, 200 centimeters, they said. Okay, so there's our, you know, so this would be for 0 less than X less than 200, and then T would be between 0 and infinity. Okay, so that takes care of our differential diffusion model. But now when you get into the boundary conditions, the top here, which I think they're saying is 0. Okay, so they're doing it this way. This is 0, this is 200 down here. Not sure why that got darker all of a sudden, but I don't know if you can tell it got darker, but it got darker to me. So the boundary conditions, see at 0, they're saying it's insulated, so the flux would be specified to be 0 there. So when we look at those boundary conditions, at the top there we have U sub X of 0, and T would always be 0. Okay, so that takes care of that. But this other, it's in a bath. And so this was a type 3 boundary condition. This one down here is going to be a type 2 boundary condition because the end is not being held at 20 degrees. It is in a bath of 20 degrees. And so the heat, well, I think this started out at 0 degrees. So it'll actually get heated up at this end and should move up through the rod. And so let's see, so in that case we have okay. Sometimes they, oh, I don't even remember what I just erased, but we're doing X and T, and that's what I had. Then 200 T. Okay, so that derivative is equal to, now they're using the H minus H over K. I think they told us, and actually they said, oh, well, usually you don't use minus H over K, you use lambda. So, yeah. They're changing things up for us here. So we'll go with the H minus K. And, or minus H over K. So this is equal to minus H over K. And it is U at 200. My parentheses all right. So, okay. And so we've got a type 3 boundary condition at one end and a type 2 boundary condition at the other end. And as they're saying, yeah, that might be very Okay, so that is a model that would describe this particular heat flow problem. So, oh, I see. So they actually, yeah, they actually gave values then for alpha squared, K, and H. So that's why we use the K and H. Okay. So then you could fill in those values, and we have everything you need to solve that problem. Alrighty. So that is a typical application in a model.